Is my screen visible? Is the screen visible?
Yes, ma'am. Yes, ma'am.
Okay.
Good afternoon, ma'am.
Afternoon. So let's start today's session. Good afternoon, everyone. Today is problem solving session 9, and I'm your TA Vidushi. So basically, in this class, we will discuss about. Firstly, we will discuss about FRAT. What is FRAT? It's the Foster Resonance Energy Transfer. That is Foster sometimes instead of Foster it can be fluorescence also. So it's Foster's resonance energy transfer. So what do you mean by flat? It is kind of dipole-dipole interactions. So basically what happens in this is if we excite a donor by giving some light, donor goes to the excited state where it reflexes back to the lowest excited vibration level of the S1 state, and from there it transfers the energy to the receptor molecule. So in the green arrow, it is showing that the donor's non-radiative transfer process, and the here in the yellow arrow, it shows the receptor's induced excitation. So these are the resonance energy transfer. While this curly arrow indicates internal conversion and vibrational relaxation. So there are various prerequisites that must be met so that we can achieve the FRET. The first condition is that the emission of the donor should overlap with the receptor's excitation. Second condition is that the orientation of the dipole. The orientation of the dipole should be optimum for the efficient FRAT to occur. Also, the distance between the donor and receptor should be less than 10 nanometers. So these are several conditions for the forced resonance energy transfer. Basically, it is a long-range dipole-dipole interactions. Now, what is fluorescence lifetime? Lifetime means that average time that a molecule remains in the excited state after the excitation, that is called as fluorescence lifetime. So here the fluorescence lifetime of a fluorophore, like you use the term chromophore, like we are talking about a fluorescence, so we are using the term fluorophore here. The fluorescence lifetime of a fluorophore is a measure of the average time a fluorophore remains in the excited state S1 after the excitation. And lifetime can be described by an exponential decay. So what do you understand by fluorescence lifetime? When you excite a donor or a molecule to a higher excited state, the time it remains in that excited state is called as the lifetime. So the lifetime differs for every molecule, and it doesn't depend upon the concentration. It depends upon the external factors that are conformation. If we just change the conformation of the protein, pH, etc. So it depends upon the external factors. But if we talk about dye concentration, photo bleaching, light scattering, excitation, light intensity, fluorescence is lifetime is independent of the dye concentration. So it doesn't matter whatsoever concentration we are taking, it will be independent to it. It only depends, or it can be changed to some external factors by changing some conformation of the protein or by pH, etc. So if you look here, in the system there is donor only. So if you will excite a donor to a high excited state, then it vibrationally relaxes back to the lowest vibrational level of the excited state and further it emits. But what happens in the presence of acceptor is that if donor and acceptor's distance is less than 10 nanometer, then there is a possibility of the non-radiative energy transfer. This non-radiative energy transfer can be flat also. So basically what happens, if we excite a donor to an excited state, it vibrationally relaxes back to the lowest vibrational level of the excited state and further it non-radiatively transfers the energy to the acceptor molecule. This is called as a frat. So now if you will look upon the exponential decay diagram of intensity versus time, this is the for the donor and this is for the donor in the presence of acceptor. So just remember that the fluorescence lifetime is independent of the concentration, photo bleaching, light scattering and the excitation light intensity. So here what do you mean by photo bleaching? This term photo bleaching, what does it mean? Anyone? Oh. यार नेट ही नहीं चल रहा है लिखा मैं बोल रही हूँ और ये नेट नहीं चल रहा है Is the slides visible?
Yes, ma'am. Visible.
There's some network issue. So should I repeat from the frat or from the fluorescence lifetime?
Ma'am, please repeat from first line.
From the frat? Okay.
Yes, ma'am.
So what is frat? Basically frat means Foster resonance energy transfer. Sometimes you will see instead of Foster, it is written as fluorescence. It's Foster resonance. Energy transfer. So basically, what do you mean by FRAT? It is a long-range dipole-dipole interaction. It is a non-relative energy transfer. What happens in that if you excite a donor, then a donor molecule gets excited to a higher excited state, suppose S1 here, then it further vibrationally relaxes back to the lowest vibrational level of the excited state, and from here it transfers the energy non-radiatively to the acceptor molecule. That is called as FRAT. So if you will see this black curly arrow, it indicates internal conversion vibration relaxation, while the green dotted arrow indicates the donor non-radiative process, that is the resonance energy transfer, while the yellow also dictates the acceptor's induced excitation. So these are the two arrows which dictates the resonance energy transfer. So there are various conditions for the FRAT. So first condition is that the donor's emission should overlap with the acceptor's excitation. That is, there should be a spectral overlap. This, if you are like looking on this gray, just a second, on this thing, gray part, this is the spectral overlap. So for a molecule to have FRAT, there should be a spectral overlap. This kind of overlap. This. So donor's emission should overlap with the acceptor's excitation. Secondly, the distance between the donor and the acceptor should be less than 10 nanometer. Also, the orientation of the dipole should be optimal for efficient FRAT to occur. Now, if we'll talk about fluorescence lifetime, what do we mean by lifetime? Lifetime is the time that a molecule spends in the excited state after the excitation before coming back to the ground state. So basically, it's the fluorescence lifetime of a fluorophore. Like here, we are talking about the fluorescence, so we can use the term fluorophore. So the fluorescence lifetime of a fluorophore is a measure of the average time a fluorophore remains in the excited state S1 after the excitation. And the lifetime can be described by an exponential decay. Also, the lifetime can vary for every molecule, and it is independent of the dye concentration, photobleaching, light scattering, and excitation light intensity. But it can vary due to external factors such as changing the conformation of the protein or pH, etc. So these external factors can affect the fluorescence lifetime, but the concentration of the dye, photobleaching, light scattering, they are independent. So if you look downstairs in this diagram, it's of donor molecule. Suppose you are exciting a donor molecule and it further goes to excited state, then it further vibrationally relaxes back to the lowest vibration level of the excited state and further it emits. But what happens in the presence of an acceptor in the donor molecule, there can be a chance of non-radiative energy transfer. Because of the less distance, that is less than 10 nanometer between the donor and receptor, there can be chance of non-radiative energy transfer. So how it happens is that when you excite a donor molecule, it goes to the excited state, then it further vibration relaxes back to the lowest vibrational level of the excited state, then further it transfers non-radiative the energy to the acceptor molecule. That is what FRAT is. So here there is a plot of intensity and time, and this, if there is FRAT in the principal receptor molecule. So you have to remember that fluorescence lifetime is independent of the concentration, but it can change due to external factors like pH, etc. So just tell me, what do you mean by photobleaching? Photobleaching. Anyone? What do you mean by photobleaching? So basically, what do you mean by photo bleaching? It is an sometimes you may see it is like called as fading also, or in simple terms, it is an photochemical alteration by which the molecule is unable to flourish permanently. That is called as photo bleaching. Now let's solve some questions. Consider,
Ma'am, can you repeat photo bleaching once?
yeah, photo bleaching is called as fading also. So basically what happens is that it is a photochemical alteration by which a molecule permanently it can't be able to flourish. So it can't show fluorescence due to some photochemical alteration. Now consider the quenching of your organic fluorescent species with lifetime of 6 nanoseconds by a d metal ion with Kq equals to 3 into 10 raised to by 8 DMQ mole inverse second inverse. Predict the concentration of a quencher required to decrease the fluorescence intensity of the organic species to 50% of the unquenched value. So basically in this question you have to determine the concentration of the quencher. So how you will solve it? You have heard of Stern-Volmer plot, I guess. So according to that, the equation is F naught by F is equals to 1 plus KQ tau into the quencher. Where what is F naught? F naught is the fluorescence intensity in the absence of quencher. You can write I also. It is in the absence of quencher. While what is F? F is the fluorescence intensity in the presence of quencher. So basically what is quencher? What does it does?
It decreases the fluorescence intensity.
Correct. It decreases the fluorescence intensity. Like maybe in the previous session we discussed about the quinidine molecule that if we add chloride ions into that, the fluorescence can be quenched. So in that case, the chloride will be act as a quencher. So now to solve this question, we will use a Stern-Warmer equation. According to it, F naught by F is equals to 1 plus KQ tau into Q, where Q is the concentration of the quencher, T is the lifetime, KQ is the rate constant. And F naught is the fluorescence intensity in the absence of quencher, while F is the intensity in the presence of quencher. So now in the question, it is written that we have to predict the concentration of quencher to decrease the fluorescence intensity to 50% of the unquenched value. Unquenched value means in the absence of quencher. That means F will equal to 0.5, like 50% is 0.5 of the unquenched value. Unquenched value means absence of the quencher, that is F naught. So F will be equal to 0.5 F naught. If you will substitute this value in this equation, then you will get F naught by 0.5 F naught equals to 1. And what's KQ? KQ is given, it's 3 into 10 raised to by 8. And lifetime is given, it's 6 nanoseconds. So basically, nanoseconds is convert, it's 10 into minus 9 seconds. And quencher you have to calculate. this thing, the concentration of energy you have to calculate. So what will be the answer after solving it? Let's solve this.
0.55
Yeah, correct. It will
moles
be
per
0.55 molar. So just remember this equation. Now we'll move to next question. What is the transfer efficiency when a donor and the receptor are separated by 0.5 R0, R0 and 2 R0? So just tell me for the first part 0.5 R0. You have to calculate the transfer efficiency when the donor and a separate distance is separated by 0.5 R0. So which formula we will use to solve it? I think we have discussed in the previous session about the energy transfer efficiency. So which formula we will apply here? Energy transfer efficiency is equals to R0 6 by R6 plus R0 6. So basically what is R0 6? What is R0 here? R0 is the R0 is the
Foster
Foster
radius.
radius, correct. And what do you mean by Foster radius? So what is Foster radius?
Distance between the emitter and the absorber.
Distance between the donor and the receptor. That is R6. That is this small r. That is the distance between donor and receptor. So what's the difference between Foster radius? So basically Foster radius is also a distance between the donor and the receptor when the energy transfer efficiency is 50%. So this is the difference. R0 is the Foster radius, that is the distance between the donor and the receptor when the energy transfer efficiency is 50%. While small r, this one is the distance between the donor and the receptor. So now in the question they are asking, you have to calculate the value of E if donor and receptor are separated by 0.5 R0. That means R is given as 0.5 R0. So here E will equal to R0 6. Substitute the value of R. It's 0.5 R0. So from here you can take R0 as a common. So it will be equal to 1 plus 0.5 whole 6 plus 1. So after solving it, the answer will be 0.9846. So just remember the energy transfer efficiency is inversely proportional to 6th power of the distance between the donor and the receptor. So is it clear? Is it clear to everyone?
Yes, ma'am.
So now just tell me the energy transfer efficiency when the distance between the donor and the receptor are separated by R naught. So just tell me what will be the energy transfer efficiency here.
0.5.
Point? Correct. It will be
0.5.
correct. It will be 0.5.
5.
So how we will solve it? It's simply E equals to R naught 6. Now we know that R is R naught. So it's R naught 6 only plus R naught 6 only. So after solving it, it will be 0.5. And just tell me what will be the energy transfer efficiency if a donor receptor is separated by 2 R naught. It's 2 R naught. It will be
0.33.
it's wrong. Just check the calculation again.
0.015.
Correct. It will be 0.015. It will be approx 0.0153. So is it clear to everyone?
Yes, ma'am.
Okay. So now we will discuss some previous assignments questions. Actually, I was looking upon previous assignment questions and maximum question are applied directly, but indirectly we have solved every question. So maybe this is of the first assignment questions. That is, in the first question, it is asked if the energy of a wave is in order of 15 electron volts, it corresponds to which part of electromagnetic spectrum? IR, X-ray, gamma rays, or radio waves? So, what will be the answer? If the energy is in order of 15 electrovolt, then to which part of electromagnetic spectrum it belongs to?
X-rays.
Pardon?
X-rays.
Yeah, it will be X-rays. Now the second question is the region of the electromagnetic spectrum used in the animal spectroscopy is microwave, IR.
Radio. Radio waves.
Yeah, it will be radio waves. So radio waves are used in the animal spectroscopy, that is nuclear magnetic resonance spectroscopy. Now, which of the following properties is not shown by a particle? Reflection, refraction, diffraction, photoelectric effect. Not shown by particle, it means, you know, there can be dual nature. It can be particle as well as the wave. So now they are asking about the wave nature. So as it is not shown by particle. So out of these four, which shows the wave property?
Diffraction.
It will be diffraction.
Diffraction.
Correct. Now MRI is the technique used to produce detailed images of the internal part of the human body. Upon which of the following this technique is used? X-ray, radio waves, IR or UV?
Radio waves. Radio waves.
So now the next question is, which of the following is not linear? X square root d square by dx square or h cap. So which operator is not linear? Which of the following operator is not linear here? The square root. Now next question. Probability density is defined as wave function, square root of wave function, square of wave function, none of the above.
Wave function.
No. Probability density we
Square
are
of the wave function.
correct. It will be square of wave function.
Square of wave function.
Yes. Now, which conditions applies for Hermitian operators? So just tell me first, what is Hermitian operator? What is Hermitian operator? It is basically a linear operator. So, Hermitian operators have real eigenvalues. They have a complete set of orthonormal eigenfunctions. They can be flipped over to other side in inner products or all of the above. So, which conditions apply for Hermitian operators? So, all these conditions are true. Just remember that Hermitian operator is a linear operator. It can have real eigenvalues. It can have complete set of orthonormal eigenfunctions, and all the Hermitian operators can be flipped over to the other side in the inner product. So the answer will be all of the above. Now next question. For a Hermitian operator eigenvalue, one can always find a complete set of eigenfunctions that are like we now only discussed.
Orthonormal.
Correct. It will be orthonormal.
Orthonormal.
Now the next question is, after n scans taken, the increase in the signal to noise ratio S by n is given by n times, n square times, root n times or 4n times.
Root n times.
Root n times. So how it came root n times? So basically we are talking about signal to noise ratio. Signal is determinate while noise like fixed value, while noise is random, it's indeterminate. So if you will look upon net signal, it is equal to the ns, where n is the number of scans and s is the signal for the single scan. So now after n times taken, the increase in signal ratio will be equal to root n s by n. So how it came, like as noise is random, so it can take any value. It can be increased value or decreased value also. So if you just take of standard deviation, it can be equal to root n into s. So if you divide these two, then the answer will be root n s by n. So after n scans, the increase in signal to noise ratio is given by root n times. Now next question is, Schrodinger wave equation is a type of non-linear differential equation, third order equation with respect to time, linear differential equation, or first order equation in space. Schrodinger wave equation. What is Schrodinger?
Linear differential equation.
What is Schrodinger equation? Schrodinger equation. Anyone? It's a kind of linear differential equation. Now, next question. Molecules containing the vibrations without the center of symmetry. Like, what is center of symmetry? Like, we will just take an example of CO2. This molecule has center of symmetry. So now,
Higher active, Raman inactive.
higher active and Raman?
Inactive.
Wrong. It will be both higher and Raman active.
German. Yes, yes, yes.
Like, like how we can say a molecule is higher active. What's the condition for a molecule to be higher active?
It should not be unsymmetrical.
There should be
There should
uh, there
be
should
center
be
of symmetry.
a change in dipole moment.
Dipole.
Change in dipole moment.
Correct. Change in dipole moment. Change in dipole moment. So the molecules without center of symmetry, that is, there will be change in dipole moment. So therefore, both will be Raman and higher active. Now, just tell me about FeCl3, Cl2, water, and helium. Which will be Raman active? Sorry, which will be higher active among these four? Higher active. Now you know about
FeCl3
FeCl3 and
H2.
yeah. Why
FeCl
chlorofluorocarbon? Yes. Like if you will see chlorine molecule, this is same like Cl, Cl. So there is
no
no
change in
change in
dipole
dipole
moment.
moment. Correct. And while helium, so
Individual atom.
yeah. So here there is no change in dipole moment. Therefore, the answer will be FeCl3 and water. Now, which of the following molecule gives a pure rotational spectrum? So just tell me what is the condition for a pure rotational spectrum? Like we already have discussed these questions the previous sessions. What is the condition for a pure rotational spectrum? It should have a permanent dipole moment.
Permanent dipole moment.
Yeah, it should have permanent dipole moment. So out of these molecules, just tell me which will have a permanent dipole moment. About N2, CO2, OCS, or H2.
OCS.
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 Correct. It will be OCS. It's me. While N2, it doesn't change dipole, like it doesn't have a dipole moment. CO2, is central symmetry molecule. H2, homoatomic diatomic molecule. So pure rotation spectra in that OCS will have a permanent dipole moment. So OCS will be the right answer. Now, the detection of homonuclear diatomic molecule. What do we mean homonucleus? Same nucleus. Like H2, N2. It contains two atoms, so they are diatomic. Homonuclear same nucleus like hydrogen, like H2, N2,
Molecule formed
O2.
by two similar atoms.
Yeah. So it can be done through, like detection can be possible through IR, Raman, microwave, or none of the above.
Raman.
Correct. It will be Raman spectroscopy. Because in IR spectroscopy, what does it tell? It tells about the functional groups like esters, aldehyde. It tells about the vibrational frequency of a molecule, stretching frequency. So various functional groups like esters, aldehyde, ketones, amines, alkynes, these all can be detected by it. So through Raman, we can detect the homonuclear diatomic molecules. Now the next question is, what is the order of vibrational frequency for CCl, CBr, CC, CO and CH? So just tell me what will the order, who will have the highest vibrational frequency or the lowest vibrational frequency?
CCL highest.
C. CL will be the highest. Why? Like we discussed this formula, I guess. Mu is equals to 1 upon 2 pi
1 upon 2 pi
under root k by mu.
k upon mu.
And what is mu?
Reduced mass.
Reduced mass. So mu is m1 m2 upon m1 plus m2. So from this you know
Yes,
that
yes,
the
yes.
stretching frequency is inversely proportional to the mass or the reduced mass. So now you know out of Cl, Br, C, oxygen or the carbon, oxygen or hydrogen, which will have a less mass.
Carbon.
Hydrogen. Hydrogen. And who will have the highest? It will be bromine.
Bromine.
Yeah.
Bromine.
So since hydrogen is the lowest mass, therefore its stretching frequency will be higher. So the option will be CH, CC, CO, CCl and CBr.
Option A.
Yeah. Now it is understood.
Yes, ma'am.
Now the next question. Earlier in the IR spectra, one wavelength was used at a time which required longer time, but this is not the case due to absence of broad spectrum of wavelength. Use of Fourier transform algorithm allows to complex time domain data to be converted to the frequency domain data. Use of slits to get parallel light or none of the above. Now what happened is that like nowadays we are using the FTIR. Earlier we used that IS factor in which one wavelength was used at a time. So it takes a lot of time. But now we use FTIR. FTIR is Fourier transform IR. So the use of FT algorithm allows to complex time domain data to be converted to the frequency domain data. That's why it's more rapid nowadays. Now the next question is the spin angular momentum and the magnetic moment are related as. So how does spin angular momentum and magnetic moment is related? There's an equation to it.
And mu directly proportional to S.
U is directly proportional to S. But how? Like what's the equation which these two can be related? You know, mu is the magnetic moment and S is the spin angular momentum. So how it can be related? Mu is gyromagnetic multiplied by spin angular momentum. This is gyromagnetic ratio. So that's why mu is directly proportional to S. Now the next question is the wave number for the first line of Balmer series in terms of R is 2R, R, 8R by 9, 5R by 36. So just solve me and tell me the answer. What will the wave number of the, just remember it's the alpha line that we're talking about, the first line of the Balmer series. That is the alpha line. So what it will be?
5R by 36.
5R by 36. Okay, it's correct. So you know this formula mu is equals to R 1 upon n1 square minus 1 upon n2 square. So what's n1 and n2? We know we are talking about the Balmer series. So Balmer series are those in which transitions occurs from the second orbit. So they are talking about the, like here, suppose this is n1 equals to 1, this is 2, this is 3, this is 4, and this is 5. So we know that the first series is Lyman and second is Balmer. So the transition occurs from the second series. Now they're telling about the first line. So what will the first line? Like transition can be from here. It can be
2 to 3.
correct 2 to 3. So this is the first line. The first line we also called as alpha line. So R is R as it is. N1 is 2. So 2 square is 4 minus N2. N2 is 3. So 3 square is 9. So after solving it, it will be 5R by 36. This will be the right answer. Is it understood? Is it clear to
Yes,
everyone?
ma'am.
Yeah. Now the next question is, in an hydrogen atom, the spin orbit coupling causes broad spectra, fine spectra, hyperfine spectra, or no spectra. Spin orbit coupling. In a hydrogen atom, they are asking. So it causes fine spectra. So the answer will be fine spectra. This one. Now, the source of radiation used in the atomic spectroscopy is mainly deuterium, hydrogen, holocathode, xenon, mercury arc lamp, or none of the above. So which radiation is used in atomic spectroscopy? It is holocathode lamp. So if I will ask like for UV, which lamps do we use for UV? UV visible spectroscopy.
Hydrogen deuterium.
We use tungsten, like for the visible range, and deuterium. So these two are lamps generally used. Case of UV visible, tungsten, deuterium. Now they were asking about the atomic spectroscopy, so it is holocathode lamp. Now 2p1 3t1 transition is not allowed to which of the selection rule? J selection rules, S, L, or Laporte? So it's Laporte selection rule. And you know Laporte selection rule is also known as orbital selection rule. So the transition from 2p1 to 3d1 is forbidden in case of Laporte. Just remember that. Now, which of the following is the principle of AAS? Like for atomic spectroscopy, you can abbreviate as AAS. So what's the principle? Medium absorbs radiations and transmitted radiations are measured. Color is measured. Radiation is absorbed by the non-excited atoms in the vapor state and are excited to a higher state. So what is the principle of AAS?
Option C.
Option C, that
Option
is,
C.
radiation is absorbed by the non-excited atoms in the vapor state and are excited to the higher state. Now the next question is, atomic absorption spectra produce narrow band with peaks generally called as lines because it involves electronic transition, vibrational transition, rotational transition, or all of the three transitions.
Rotation.
We are talking about atomic absorption spectroscopy.
Electronic only.
Correct. It will be electronic transition only. Now, the next question. In atomic emission spectroscopy, the graph is between. So there is difference. Earlier it was atomic absorption, now it is atomic emission. So the graph is between
Emission also concentration.
emission versus.
Emission versus wavelength.
Concentration.
No, it will be emission versus wavelength. Yeah, correct. Concentration. It is not concentration, it is wavelength. So just remember, in atomic emission spectroscopy, we plot emission versus wavelength. Like if I will talk about UV, so the graph is between in UV. Graph is in between for the ultraviolet spectroscopy.
200 to 4.
On the graph,
Absorbance versus concentration.
correct. It will be absorbance versus wave. Absorbance versus
Concentration.
absorbance versus wavelength. So now, which of the following is true about quantum dots? But quantum dots, they're insulators, they are semiconductors of nanoscales, they follow classical mechanics, or none of the above. Quantum dots,
None of the above.
wrong. Quantum dots are in nanoscales. So these are basically semiconductors of the nanoscales. Now, next question is, on increasing the pH, phenol shows. So what is phenol? It's benzene ring with the OH group.
OH group attached to benzene.
And OH group is attached to benzene ring. So if you're increasing the pH, then what will phenol shows? Hypsochromic shift, blue shift, red shift, or none of the above?
Blue shift.
Blue shift. Why? See phenol, they're asking about phenol group. So basically, if I properly draw the structure here,
Absorption in higher wavelength.
absorption in higher wavelength. And then higher wavelength means
Redshift.
red shift.
Shift.
Why red shift? What happens is that on increasing the pH means they're talking about basic conditions. So what happens in base? Base can abstract a proton. So phenol can form phenoxide ion. It acts as a phenoxide ion. Now what happens is that the negative charge of the oxygen can be delocalized. Can delocalize now. So now you know if it is delocalization, then the energy gap. What happens to energy gap on delocalization?
Decrease.
Correct.
Decreases.
Energy gap decreases. So if you know that energy is inversely proportional to wavelength, we know this formula.
Wavelength.
Wavelength.
We know this formula equals to h mu, that is hc by lambda. So we know that energy is inversely proportional to wavelength. So what does it mean? If energy is decreasing, then wavelength will increase. And we know that what is redshift? Redshift is that when absorption shifts to a longer wavelength. And what's blue shift? Blue shift is that in which it shifts to a shorter wavelength. So this will not be the answer. So on increasing the pH, phenol shows red shift, means longer wavelength. Is it clear? Is it clear?
Yes, ma'am.
So just remember that whenever you are talking about delocalization, if there is more delocalization, the energy gap will decrease. And due to that, the wavelength will increase. Now, the absorbance spectra are a plot of absorbance spectra are a plot of absorbance versus
Absorbance versus wavelength.
wavelength. In a cyclic conjugated molecule, conjugated means double, single, double bond. So, in conjugated molecule, the resonance condition for an electron to resonate is 2 pi r equals to n lambda, 2 pi r equals to n by lambda, pi r equals to 2n lambda, or pi r equals to n lambda. So, in a cyclic conjugated molecule, resonance condition for an electron to resonate is so what will the answer? What was the answer for that? Like, what is the resonance condition for an electron to resonate? It will be 2 pi r equals to n lambda. Now the next question is the energy gap in quantum dots. Like we already discussed, what were the quantum dots? They were semiconductors. So the energy gap in quantum dots dash with dash in size of quantum dots. It increases, decreases, no change or decreases. So what happened to energy gap with respect to the size of the quantum dot? It is,
Increases with decrease.
yeah, it is inversely proportional. So if the energy gap will increase, then the size of quantum dot will decrease. Now, in a quantum well, the electron is confined to how many dimensions? 1, 2, 3, 4.
One.
Quantum well, like electron is confined to only one dimension. Now, what will the order of the lambda max for n to sigma star transitions? So you know what are the transitions involving
Ma'am,
between?
hello, hello,
Yes,
hello.
Yes, you're audible.
Ma'am, electron is confirmed how many dimensions means one electron is in one orbital, one is upward direction and one is downward direction, na madam.
Electron is single electron, na?
And a quantum. Oh, okay, madam. Okay.
Now just tell me for the second question. Just tell me the answer for this. The lambda max for n to sigma star transitions. So now you know, like, now you know that. Just a second. What are the transitions that are involved? Like it is. It is going. Like sigma, then comes pi, then comes non-bonding of the p orbitals, non-bonding orbitals, then it's pi star, then is sigma star. So you know the sigma star has the highest energy. So they are arranged in order of increasing energy. So now they are talking about N, that is non-bonding to sigma star transitions. Basically, they are talking about alcohol. RSH and RNH, that is amine. Now if you look upon oxygen, sulfur and nitrogen, they all have lone pairs. They all have lone pairs. So these lone pairs are the non-bonding electrons. Because they're not taking part in bonding, and that's why they're non-bonding. These lone pairs on oxygen, sulfur, nitrogen. So now just tell me what will be the order of lambda max for the n non-bonded to sigma star transitions. So the electron is going from non-bonding orbital to the sigma anti-bonding orbital. So what will be the answer?
RSH greater than RNH2, then ROH.
So why it will be RSH? Like why you are seeing that for the RSH the lambda max is greater?
Electronegativity decreases down the group.
Okay, electronegativity decreases down the group then. Like if you
And
see
it
your
has an
P,
additional
yes,
orbital.
like it's carbon, nitrogen, oxygen. So here electronegativity of oxygen is more than nitrogen. What happens is that on electronegativity, suppose your homo-LUMO gap is here. Like suppose for oxygen and for nitrogen. But you know that oxygen is more electronegative. So what happens is that electronegativity decreases the energy. So you were thinking that HOMO level is here, so it will be slightly decreased. But so electronegativity decreases the energy gap. Nitrogen is less electronegative, so there will also be decrease, but less than oxygen. So remember that if electronegativity decreases the energy gap, decreases the energy. So if the level are here, for oxygen the level will decrease. As oxygen is more electronegative, so more decrease will be observed for oxygen. So for that reason, RSH will have a higher. Secondly, the energy gap is very less in case of RSH. That's why wavelength is maximum for RSH. And energy gap is more in ROH. Therefore, lambda value is less in ROH. Just remember that, like in all this, just you have to remember these 2 points, that electronegativity decreases the energy. Now, an example of radiative de-excitation is fluorescence, internal conversion, intersystem crossing, or vibration relaxation.
Fluorescence.
Fluorescence. Like if you see Jablonski diagram, suppose your molecule is in ground state. And this is the electronic level, while these are the vibrational levels of the ground state. And similarly, they are the vibration levels of the excited states. Suppose if you excite a molecule to a higher excited state, so basically what happens is that the molecule can go to any vibrational band of the excited state. But then it further, the molecule from the higher excited state, it relaxes back to the lowest level of the lowest vibration level of the excited state. Similarly, from here, it will relax back here. From here, it will relax back here. So this is vibrational relaxation. This is vibrational relaxation. Now, if a molecule from here, it will come to ground state, it will emit some light and it will form of radiations, that is called as fluorescence. It is fluorescence. While now you know this molecule is in singlet state and there is another level that is lower of that has a lower energy than singlet, that is triplet state. So if a molecule goes from singlet to triplet, it goes via intersystem crossing. So the transition from singlet to triplet is called intersystem crossing. Now you know that if a molecule goes from, suppose it's S1, it's S0. If a molecule goes from S1 to S0 state, it is termed as fluorescence. While if a molecule goes from a triplet state to ground state, it is phosphorescence. So from here it will be phosphorescence. Please you can expand now. So this is phosphorescence. And just remember that there are 2 types of transitions, radiative and non-radiative, where fluorescence and phosphorescence are the radiative transitions, while intersystem crossing, internal conversion are the non-radiative transitions. Like vibrational relaxation, these all are non-radiative transitions. So what happens in vibrational relaxation, the energy is lost in the form of heat. So there is no radiations. But what happened in radiative transitions? There are radiations, and the example can be fluorescence, phosphorescence. So in the question they were asking about example of radiative de-excitation. So the answer is fluorescence. Is it clear? Is it clear?
And if option contains
Yes, ma'am.
phosphorescence, will that be also answer?
Yeah. Both will be the correct option.
Okay.
Similarly, these three are the non-radiative transitions. Now, next question is, which of the following has a longer lifetime? S1, that is singlet, S4, T is triplet, or S2. So, just always remember that triplet state have a longer lifetime than the singlet state. Doesn't matter in which singlet state it is, like S1, S4, S2, but longer lifetime. Lifetime means, like we already discussed, what is lifetime? Lifetime is the time that a molecule stays in the excited state before coming back to the ground state. Like after excitation, the time that a molecule spend in the excited state is the lifetime. So out of these, the lifetime will be longer in case of triplet state. Is it clear?
Yes, ma'am.
Now, next question. What is the correct order of the lambda max for N to pi star transition for Cn, Rn2, Rn double bond Nr? So lambda max.
First option.
First option.
First option.
Why? Why?
CNS triple bond.
So basically, if you will compare these two, RCN, RNO2, it can be N plus O minus or like on, or it's RN double bond NR. So how if you will compare these two diagrams, so these three molecules, so you can see there is difference in electronegativity. And you know that it's sp3 and these are these sp2 sp3 is single bond, sp2 is double bond, sp is triple bond. So it is sp hybridized, it's sp2 and it is sp2. So out of these the like electronegativity, remember that wavelength increases the with increase in electronegative group, or like we discussed now, like electronegativity decreases the energy. So if there is decrease in energy, so wavelength will be maximum. So now in the first example, like this sp2, sp2 has higher electronegativity, therefore this one, out of these three, this one will have a higher electronegativity, therefore lambda max will be higher. Then comes Rn2, then comes cyano group. So based on electronegativity difference, the lambda max is higher for this moiety, as in this electronegativity is also higher. Is it clear? Like if you're solving these kind of questions, just remember, like for the lambda max, that energy is inversely proportional to wavelength. Secondly, electronegativity decreases the energy, and if you increase the delocalization, then energy gap decreases, therefore wavelength increases. Is it clear?
Yes, ma'am.
Now, which of the following does not show fluorescence or fluoresce? quinine sulfate, chlorophyll, ethylene bromide, nucleic acids. Why it will be nucleic acids? Just tell me. Firstly, just tell me what are the conditions for a molecule to be fluorescent. Like how can you like if I
It
like
should be rigid.
it should be rigid, correct? Then
Should have delocalized electron intensity, good overlapping,
correct. Intense absorption band,
lifetime should be shorter.
correct. Lifetime should be
Stated
shorter,
lifetime should be
correct. It should be rigid. There should be shorter lifetime, shorter excited lifetime, rigidity, intense absorption bands, and delocalized electrons. So if you will see like in a chlorophyll molecule, it's a conjugated system, and in which the central atom is like which is central metal in case of chlorophyll,
magnesium.
correct. It is magnesium, and with quinine sulfate and ethylene bromide. So out of these nucleic acids, and what are nucleic acids? Like an example of nucleic acid,
DNA and RNA.
DNA, RNA, deoxyribose nucleic
DNA.
acid, and ribose nucleic acid. So these molecules does not show fluorescence. So just remember the Jablonski diagram. Now, next question. Which of the following is true about fluorescence spectroscopy of a molecules in the UV visible region? Emission usually occurs at energy that are equal to the energy of excitation. Emission usually occurs at energy that are less than energy of excitation. Emission usually occurs at energy that are greater than energy of excitation, or none of the above.
Second option.
Second option. Why?
There will be increase in the wavelength, emission wavelength. Energy is inversely proportional to wavelength.
Like here we can explain like suppose a molecule is in ground state and this is your excited state. So there are also vibrational bands. Similar vibration bands are here also. So if you excite a molecule in the ground state, it goes to a higher excited state, then this much energy. So you know for a molecule absorbs this energy, then it goes to a high excited state. So it is the energy of absorption. Now molecules vibrational relax back to the lowest vibration of the excited state, and from this state it undergoes emission. So this is your energy of emission. So now you know energy of absorption is higher than energy of emission. So similarly, wavelength of absorption is less than wavelength of emission, as energy of absorption is more than energy of emission. Therefore, lambda of absorption is smaller that is lambda emission is longer. Therefore, emission always occur at longer wavelength. So, emission usually occurs at less energy than the energy of excitation. Is it clear? Is it clear?
Yes, ma'am.
Now, what are the main advantage of fluorescence over UV? Its compatibility with most analytes, its sensitivity, its compatibility with separation techniques, none of the above.
Sensitivity.
Sensitivity, correct. Now next, why must the radiation source for fluorescence spectrometry be more powerful than for absorption spectroscopy? The magnitude of the output signal is proportional to the power of incident radiation. The sample won't fluoresce if the incident radiation is of low power to allow for scattering by the sample. None of the above. So what was the answer?
Option A.
Correct. It will be option A. The magnitude of the output signal is proportional to the power of incident radiation. Next, why phosphorescence measurements are usually made at low temperature? You know now phosphorescence is transition from triplet to ground state. So why these phosphorescence measurements are made at low temperature? To prevent thermal degradation of the phosphorescent species, to promote phosphorescence by slowing the rate of radiation-less transfer process, to increase the efficiency of the detector, to decrease the efficiency of detector. Like phosphorescence is the radiative transition, and there can be non-radiative transition also in a molecule. To slow the rate of non-radiative transitions or radiation-less transfer process, we measure phosphorescence at low temperature. Is it correct? Now next question, protein concentration cannot be determined using Benford assay, BC assay, MTT assay, Lowry assay. What is the answer?
MTT assay.
90
MTT assay. Now next question, what happens to the fluorescence intensity if the molecular weight increases?
Decreases.
Why? Why? Because
Changes.
if molecular weight is increased, then your frequency polarization also increases. And what's frequency polarization? Is the motion, rotational motion of your molecule. So, therefore, fluorescence intensity will decrease if molecular weight increases. The fluorescence wavelength is often much longer than the irradiation wavelength that we have seen now. If the emission is longer, like emission wavelength is longer than the absorption wavelength. So it is a consequence of which phenomena? Frank cordon, low extinction, vertical transitions, or high intersystem crossing rates. What is the answer?
Frank on principle.
Correct. It's a Frank cordon
Frank on
case.
principle.
So up to this, is it clear?
Yes, ma'am.
Now we will solve some questions. Let me take a new slide. About ground state term symbols and all. Now, like maximum questions have been covered in the assignment. Like in this session, I have covered maximum questions, and rest of the questions are already covered in our previous sessions. So I'm not going to repeat that. Now I will revise what we have learned for the ground state term symbols because it's an important topic. Some questions can come. So just tell me for D2 system. For the D2 system,
3f2.
It will be 3f2. So D2 system 2 means there are 2 unpaired electrons. So in D there are 5. So option 1, 2. 2 means there are 2 unpaired electrons. The ground state term symbol is represented by 2s plus 1. L, J. So spin, how much is the spin? Like there are 2 unpaired electrons, so half
1.
plus half is 1. 2 into 1 plus 1. That comes out to be 3. And what's L value? L value you can know S, P, D, F. So 0, 1, 2, 3. So for D, L value is 2. Sorry, for D, L value is 0, 1, 2. Like for free metal ion, we will use this formula, not this one. It will be 2 into 1 plus 1 into 1. So it comes 2 plus 1, that is 3. And for 3, it's F. So it will be 3F. And J value, it ranges from L plus S to L minus S. As L plus S we use if the electron is more than half filled. As it is less than half filled, so L minus S. So it will be 3 minus 1, that is 2. So answer will be 3F2. Now just tell me for D5 system. D5 system. D5.
6s 5 by 2.
Correct. It will be 6s 5 by 2. And for D7,
4f 9 by 2.
4f 9 by 2. Correct. D9, D9. Just tell me for D9 and D6. D6, D or D9.
2d 5 by 2.
For D9 it is
2d 5 by 2.
correct. It's 2D 5 by 2. And just tell me for D6 and D8. So what will be the value for D6? For D6.
Ma'am, could you explain this once again, ma'am?
Like for what? D9 or D7?
The basics. I was not knowing this concept.
Actually, I think you have not attended the previous session. Okay, I will repeat it again.
No, ma'am. I have missed this, I guess, ma'am.
Okay, I will repeat it. So basically, we are calculating the ground state term symbol. So how we will represent these term symbols? It is represented by 2s plus 1 L, then J. First 2s plus 1, S is the spin. You know, the spin can be half or minus half. Like if it's the spin is half, and for here the spin is minus half. And 2s plus 1 is the spin multiplicity. Spin multiplicity. L is the orbital angular momentum and G is the total angular momentum. So basically now if you see example of D6. So D6 means there are 6 electrons in the D system, in the D cell or the D orbital, and you know D orbitals can maximum occupy 10 electrons, and there are 5 subshells. So now fill the 6 electrons. So how 6 electrons can be filled? Firstly you will singly occupy each shell, then you fill the remaining. So here so here you can fill the 6 electrons as we are talking about the D6. Now what will the spin? Here we are talking the spin, like total spin. So see here, as there are 4 unpaired electrons, like these are paired, so the 4 paired half plus minus half, it's cancels out.
Yes, ma'am.
So these are 4 unpaired electrons. The total spin will be 4, and you know for each electron the spin is half. So the total spin, as there are 4 electrons, so it is 4 by 2. That comes out to be 2. Now for the spin multiplicity you have the formula 2s plus 1. That is 2 into 2 plus 1, that is 5. Is it clear? So it is 5.
Yes, ma'am.
Now how you will calculate the L value? So here it's 0, it's minus 1, it's minus 2, plus 1 and 2. So just write these two. How many electrons are there? 2. Now in the first one it is 1 electron plus 1 into 1. Now in 0 it is 1 plus 0 into 1. So in then plus again, then in minus 1 it's 1 electron plus, and in minus 2 also it is 1 electron. So it comes out to be 2 into 2 4 plus 1 into 1 1, 0 into 0 is 0, minus 1 into 1 is minus 1, and minus 2 into 1 is minus 2. So this cancels out, it comes out 2. So now see, if you look here, 2 corresponds to D. So it will be L value is D, 5D. Is it clear up to this?
Yes, ma'am. Yes, ma'am.
Now J value. J value, you know, it ranges from L plus S to L minus S. As you know, total 10 electrons can be occupied in D, and there are 6. So it is more than half filled. So we will use L plus S. Suppose if the electrons were less than half filled, then you will use L minus S. And if it is exactly half filled, then J will be equal to S. So just remember these three formulas for solving J value. Now it is 6, that is more than half filled. So for J you will use L plus S. Now L value is 2 and S value is also 2. So it is 4. So the ground state term symbol will be 4D4.
Yes, ma'am. Thank you, ma'am.
Yeah. Now just solve and tell me for D8 system. The D8 system.
I'm 3F4.
Correct. It is 3F4. Now the last for D10. Just tell me for the D10. 3F4. Now last for D10 system.
Yes.
Yeah. It will
2D
be.
5 by 2.
I am not asking 2D fiber to D9. Na? I am asking for D10. You have 10 electrons, 10 unpaired, 10 electrons. That means everything is paired. There is no unpaired electrons.
1s.
Correct? 1s, and what will be the J value? J value, simple.
1/2.
Huh? J value. J value is
1. 1.
why 1?
From
J
0.
is 0. Yeah, it will be L plus S, na? So it's 0 plus 0. All the electrons are paired, na? So spin will be 0 here. And L value will also be 0. Why? Because everything will cancel, like 2 into 2 plus 1 into 2 plus 0 into 2 plus minus 1 into 2 plus minus 2 into 2. So everything will cancel out. The final answer will be 0.
Yes.
Yeah.
Yes, ma'am.
Now if I will ask you for the diatomic molecules, like we discussed now, for the diatomic molecules also, how we can know the term symbol. So just tell me for lithium ion. For the lithium, what will the term symbol? Now we know the Like for these diatomic molecules, there's slight variation in the term symbols. So, what is the term symbol for lithium? Like we generally represent by 2s plus 1 lambda g slash u in this manner. So for lithium, just tell me what will that term symbol, ground state term symbol. We have done this in our previous sessions. Lithium 2. So basically there are two lithium atoms, na? So what will the term symbol? Anyone? Like we have already discussed this multiple times. For lithium,
1s.
we don't use S for the term symbols. Like for the diatomic one, what do we use?
Sigma.
Then, and it's zeroed or unzeroed? It's zeroed or unzeroed? As orbitals are always symmetrical, zeroed. And you know, if we are using sigma, then we have to use plus or minus. Why I'm using plus here? Because minus we only use when electrons are in pi orbital. As no
Pi
electrons
orbital.
is
Pi
yeah,
orbital.
as no electrons are in pi orbital, so we use plus. Now just tell me for helium, or like just tell me for helium 2 plus.
Two sigma mu.
Correct.
Sorry. 2 sigma mu plus.
Correct. It's 2 sigma u plus. And if I am asking for suppose manganese ion, manganese 2 positive ions. So just tell me the ground state symbol for this. Mn2 positive. Just tell me the value in terms of 2s plus 1 and the ground term. So what will the value? Mn2 positive.
Six SI by two.
6 is correct. And for copper 2 positive,
Ma'am, here we will not at J value.
J value you can calculate it. Now, like I have not asked. J value what will be? L plus S, so it will be 0 plus 5 by 2, it's 5 by 2 only. Now for copper 2, it's exactly half field. So it will be L equals to S, so it will be 5 by 2. J equals to S, so it will be 5 by 2. Copper 2 positive,
2D.
correct. It will be 2D. Now I guess you can solve these kind of questions. So I will just revise what we have discussed in today's session. So we discussed about FRAT. So what is FRAT? FRAT is a non-relative energy transfer. Some prerequisites that must be met to achieve FRAT, that there should be spectral overlap, distance should be less than 10 nanometer, orientation should be optimum to each other, so the dipole orientation. Also the energy transfer efficiency is inversely proportional to 1 by 6 times of the distance between the donor and the receptor. Then we discussed about the lifetime. That what is lifetime? Lifetime is the average time a molecule or a fluorophore remains in the excited state after the excitation before coming back to the ground state. And make sure you will remember that fluorescence lifetime is independent of the concentration and depends on the external factors such as pH or if you are changing the conformation of the protein. Then to know the concentration of a quencher, you use this formula F naught by F, that is equals to 1 plus KQ tau into concentration of quencher. So this formula you have to remember. Second thing you have to remember is that what is Foster radius? Foster's radius is the distance between the donor and acceptor when the energy transfer efficiency is 50%. So it can be equal to E equals to R naught 6. This is Foster radius R naught, and small r is the distance between the donor and receptor. This formula you have to remember. And make sure you will remember that F naught is the fluorescence intensity in absence of quencher, and F is the fluorescence intensity in presence of quencher. Then these were some of the questions that we solved. Then for IR, always remember that a molecule can be IR active only if there is change in dipole moment. Secondly, a molecule without center of symmetry are both IR and Raman active. Then what's the condition for a pure rotational spectrum? That a molecule should have a permanent dipole moment. Then only molecule will be called as a pure rotation. Like it will show pure rotational spectrum, permanent dipole moment. Then homonuclear diatomic molecules can be detected through Raman spectroscopy. Then for vibrational frequency, you know that vibrational frequency is inverse of reduced mass. That is, you know this equation, mu equals to 1 upon 2 pi under root k by mu, where k is the force constant or mu is the reduced mass. So stretchy frequency, if you will increase it, then reduced mass will decrease. So in this question as CH, the hydrogen has a very less mass. Because of that, stretchy frequency is highest for CH and lowest for CBr. Then nowadays we are using FTIR, and why it is so rapid, as it converts the complex time domain data to frequency domain data. Then we discuss like how spin angular momentum is related to magnetic moment. So how it is related? The magnetic moment is equals to the multiplication of ferromagnetic ratio and the spin angular momentum. Then how can you detect the wave number for the first line of Balmer series? First line means you're talking of the alpha lines. So wave number is given by mu equals to R into Z, like, and 1 upon n1 square minus 1 upon n2 square. So now you know it's Balmer series. So Balmer series, the transition is from the second orbit and the talking first line, so it will be from 2 to 3. Then what's the principle of atomic spectroscopy? That radiation is absorbed by the non-excited atoms in the vapor state, and then they're excited to the higher state. And in that, the radiation that we use, or the lamp source we use, is a hollow cathode lamp. Then transition of 2p1 3d1 is not allowed due to the Laporte selection rule. Laporte selection rule is also called as orbital selection rule. Then in atomic AA spectroscopy, we observe electronic transition only. That's why we see peaks as lines. Then in AES, the graph is between emission versus wavelength. Then what are quantum dots? Quantum dots are basically semiconductors of nanoscales, and we have discussed like on increasing the size of the quantum dots, the energy gap decreases, or vice versa. So they're inversely proportional. The energy gap increases, the quantum dot decreases in size of quantum dot. Then we discuss why a phenol molecule shows increase in pH. It shows a redshift. Why? Because you know, if we increase the pH, then it's some alkaline condition. Therefore, the base will abstract the phenolic hydroxide proton, so it will be like being as a phenoxide ion. So the negative charge on the oxygen will be delocalized. As we know, delocalization, energy gap decreases. Therefore, the wavelength increases. That means it's a redshift towards a longer wavelength. Then absorption spectra we plot against absorption versus wavelength. Then for the lambda max, we know how what will the order for the lambda max, that R is usually have the higher, because electronegativity decreases the energy. Therefore lambda max will be higher for this, not this one for the RSH. Okay, so this is. Then we know that there are two types of transition, radiative and non-radiative. Out of these, fluorescence, phosphorescence are the radiative one, and internal conversion, intersystem crossing, and vibrational relaxation are the non-radiative one. And remember that triplet has a longer lifetime than the single state. And also emission always occurs at energy lesser than the energy of excitation, or you can say wavelength of emission is higher. That's why emission always occurs at a longer wavelength. Then advantage of fluorescence over UV is in terms of sensitivity, that fluorescence is more sensitive than UV. Then about what's the difference between fluorescence and phosphorescence? In fluorescence, the transition is from the single state to the ground state, like S1 to S0, while in phosphorescence, the transition is from the triple state to the ground state, from T1 to S0. And why we always measure phosphorescence at low temperature? Because we know that along with radiative transitions, we have non-radiative transitions as well. So if we measure at low temperature, so the rate of radiation-less translucence decreases, therefore phosphorescence increases. That's why we always measure phosphorescence at low temperature. Then fluorescence intensity goes on decrease if molecular weight is increasing as the fluorescence polarization increases. Then why is it so that emission wavelength is longer? It is a consequence of the Franck-Cordon principle. Then protein concentration cannot be determined by MTT assay. Generally determines the metabolic activity. So this all we discussed. So any doubts? Any further doubts?
No, ma'am.
So now, do you need any kind of improvement or recommend like improvement session, or like in the previous session, like someone was telling me like about the assignment questions, but now like if you will see like these all questions we already have discussed indirectly, or some questions were directly discussed in previous sessions.
Hello, ma'am.
Yes.
Ma'am, can you explain the previous last week's assignments?
Yeah, I
Like
have
some
already
questions.
discussed here. Like up to now, the like all previous assignments have been discussed in today's session. The questions whichever was not, I've been discussed in the previous one. Now I have discussed it. If you want some
Okay,
specific
ma'am.
question, then just send those questions in the chat box. Like these questions, like today I discussed now, it was directly from your previous assignments only.
Ma'am, can you please share your email ID so that I can send you that questions?
I think we have that portal now, like the problem solving session in which you can ask some questions.
Oh, okay, ma'am. Okay. Thank you.
Yes. Any further doubts?
No, ma'am.
So if you want any further improvement in the session, you can tell me. Like are the sessions helpful for you, or do you need any kind of additional information or something?
Ma'am, the sessions are good, but the last week assignment, I feel it was very tough.
Actually, that assignments I am not making, that instructor is making. Like, my role is only just to solve the assignments or like some doubts, the problem solving sessions.
Okay, ma'am.
Yes. So that's all for today. Thank you.